My name is Castillo, and I'm applying for a PhD in mathematics at the Courant Institute of Mathematical Sciences. So a little bit about myself. I'm from the East Coast. I did my undergrad at NYU Poly, and I got a BS in mathematics. I graduated in 2012, and then I was commissioned in the Navy, and was in the Navy for 5 years. I was on a submarine for 3 years, and I've since gotten out. Been out for about 2 months now, and I'm applying for grad school. So why do I want to get a PhD in math? Well, it's pretty simple in my mind. I love doing it. I love reading about it. I love thinking about it. And it's something that's been there for my entire life. As a young kid, a young child, to through high school, college, as well as in the Navy. I spent quite a bit of time in the Navy learning new ideas that I hadn't gotten to in undergrad, such as general relativity, classical field theory, symmetry, and stuff related to mathematical physics, which is what I like. I hope to get into mathematical physics, and I'd like to study dissertation study partial differential equations. So I'm going to talk about complex analysis. So I think complex analysis is probably one of the richest fields that we have. There's a lot there. There's great application in electrical engineering. You have phasors, Laplace transforms, Fourier series, Z transforms, and a lot of very, very useful tools for real world modeling. And then you also have the abstract side. You have group theory, you have conformal mapping, you have harmonic function theory, Möbius transformations, hyperbolic geometry, applications to relativity. So there's a lot there, and it all comes from humble beginnings, just the complex numbers, and then it just emerges. So I'm going to talk about conformal mapping. So if you recall, conformal mapping is an analytic function such that its derivative is non-zero, and it's got some properties. It's angle preserving. So if I map the angle, if I map two arcs whose angle is some value, then the image of those two arcs under the mapping is that angle is going to be preserved. So with that simple requirement, a lot of useful ideas they emerge. So let's consider a function that's conformal from a region dz, so this arbitrary weird-looking region, to a disk dw. And let's also consider a function phi, that's a harmonic function in this disk dw. Okay, and we can solve that we can solve the Laplace equation in the disk. It's not too hard to go to polar coordinates, and it's pretty well understood. And let's say we have the boundary conditions phi. Let's say we know the value of the function on the boundary, or we know so these are the Dirichlet conditions, and these are the normal conditions. We know that the normal derivative is equal to 0. So the nice thing about this is if we define this new function big H such that it's a mapping from dz into R, or phi, which is a mapping from dw into R. The conformal mapping will preserve the boundary conditions such that H on the boundary of dz is equal to phi naught, and H is harmonic, and it also satisfies the Normand conditions. D by dn, the boundary is equal to 0. All right, so I'm going to talk about this as it relates to my favorite transformation, which is the Joukowsky transformation. So in complex for fluids, we have application of complex variables. We define this flow function, which has two components, phi and psi, and those components has to be analytic. So they're harmonic conjugates, and when we plot them, when we plot the level curves, they're orthogonal. So this is the potential function, this is the stream function. This tells me the energy at a point, this tells me the direction in which the particle is going to flow. So if I use this idea of studying boundary value problem, this function, z plus 1 over z, will map a disk into the profile of an airplane wing. And with this idea of stream, right, I know how to solve the stream flow around this disk because I can apply this function. I know the stream flow around the airplane wing. And I can actually show that the pressure below is greater than the pressure above. So PL is greater than PU, and that gives me lift. It's been a pleasure. Thank you for your time, and I hope to attend